Hi there, welcome to Math C27, Introduction to Topology. Today we're going to talk about the notion of compactness, which is one of the most powerful notions in topology. It comes up absolutely everywhere in logic, functional analysis, and every area of mathematics, and it's one of the gifts of topology to mathematics. So let's get started. What are our learning objectives for today? We're going to explain the notion of compactness informally. We're going to state the formal definition of compactness. We're going to design open covers with properties needed to prove theorems about compact sets, and we're going to use continuity and compactness in proofs. So our big motivating question for today is, what is the idea behind the extreme value theorem from calculus? Right, in Calc 1 we proved that any continuous function on a closed interval has a min and a max, and it turns out that the idea behind this is compactness. So that'll be our end goal today as we learn about the theory of compactness and how it relates to open covers. We're going to use a couple different tools today. We're going to use the notion of a limit point of a set. So we say that L is a limit point of S if every open set U containing L does what to the set? Well, we need that every open set U containing L intersects S. So every open set that has L in it also meets the set S. A set S is closed if S does what to all its limit points? We say that a set S is closed if S contains all its limit points. A set is bounded if it is contained in negative n to n for some very large n. And we're going to write ui without an index to save a little bit of space on the slides. So when we write ui, we're really thinking of a collection of a whole bunch of different ui's all in one big set together, but we're leaving out that index set to save space. And for the purposes of today's talk, everything is going to happen in the real numbers with the usual topology so that we can move along with the exposition a little bit faster. So first we need to introduce the notion of an open cover. An open cover of S is a family of open sets ui such that S is contained in the union of those open sets. So let's have a look at one. Which of the following is an open cover of the real numbers? So take a moment, look at each of these options and see if you can figure out which ones cover all of the real numbers. So our first set A is not going to be an open cover. It's not going to be an open cover of the real numbers because it misses all of the integers n. Right? These sit right beside each other. But notice that they have little gaps in between them that would not contain the integers. Our next set of intervals actually is an open cover, and it's a very important open cover because all the sets are contained one in the other. It looks something like this. Right? For any real number, it's eventually going to be bounded by some n, and will be contained in the set negative n to n. Our next set is an open cover. It's a very special open cover. It's got uncountably many elements. Every real number x is contained at the center of one of these intervals. So here we have a number x, and it's going to be contained in the center of the interval from x plus 2 to x minus 2. So this will wind up covering every real number many, many times. Now what about our last set here, D? Is this an open cover? It's not going to be an open cover because it contains no negative numbers. Right? All of the numbers here are positive, so it'll never cover a number like negative 7. Right? We're going to have a whole bunch of sets that grow like this, but they never will contain any of the negative numbers. So this will not be an open cover of the real numbers. So I hope this gives you a little bit of a feel for what can be an open cover, what might not be an open cover. Now we're going to get into the notion of a subcover. So if we have a cover of S, and we pick out some of the sets from that cover, and it still covers S, we're going to get what's called a subcover. So here's a collection of sets that cover these black points. Okay, so these are open sets in the plane. Notice how they kind of overlap in complicated ways. And now we're going to start picking out a subcover of this cover. So let's get rid of those two open sets. And maybe this guy, because he's not covering anything really. Get rid of those. I'll get rid of this one too. And now what we have left is a subcover of our original cover. Right? We've taken a collection of open sets, we've removed some of them, and now we have a smaller collection of open sets, a subcover that still covers the black points. So subcovers are central to our definition of compactness. A set is compact if every cover of S has a finite subcover. So what compactness lets us do is it allows us to take every infinite cover and pass to finite subcovers. A very, very powerful move. So let's have a look at an example of a compact set. Any finite set is compact. So suppose we have a set S with finitely many points Sk, and we have an open cover of S. What we need to do is we need to give an algorithm that'll pick out a finite subcover. So S is contained in the union of the open cover. So we can pick a U1 that's going to contain S1. Right? We can say S1 is covered, so there has to be some UI that covers it, so let's call that U1. Now S2 is covered, so we can pick a U2 that contains it. And in general, for Sk in our set, we can pick UK that covers it. But we've only got finitely many points to begin with. So we're going to obtain a finite collection of open sets that cover our set S. So we can see that any finite set is going to be compact. Now, whenever you're introduced to a mathematical notion, it helps to know an example of it, but also to know something that is not an example of it, because that lets you draw the distinction between when things work and when things don't work. So an example of a set that is not compact is the real numbers. So we want to argue that there are covers of the real numbers that have no finite subcovers. So consider the following cover. We're going to let un be that range from negative n to n, just like we saw previously. So our sets look something like this. And if this had a finite subcover, then it would have finite length. Right? We'd have finitely long segments, but we know that R is infinitely long, so we can't possibly get a finite subcover. So these two examples are very important. They motivate what it means for something to be compact. Something is compact if it looks like a finite set. Somehow it only has finitely much stuff. Things that are big and infinitely long generally tend to not be compact in the real numbers. Okay, let's move on. Here's a bit of a more exotic example. So this is going to be an infinite set that winds up being compact. So what do we have? We have 1 over n for all values of n, and then we have the element 0. So here's a diagram that represents this set. So what are we going to do? We're going to have some cover, so let ui cover S. And what we need to do is we need to argue that this has a finite subcover. So if we look at the point 0 here, it's going to be covered by some set. So we'll call this U1. So 0 is covered by U1. And now notice that 1 over n converges to 0. the limit as n goes to infinity, 1 over n is 0. So what that convergence means is that infinitely many points of this sequence are going to live inside the set U1. Thus, 0 union 1 over k, for k bigger than some large number n, is contained in U1. Right? So infinitely many of our points 1 over n are contained inside U1. So now there's only finitely many that still need to be covered. There's only finitely many terms out here that still need to be covered. Right? So this collection here is finite. And we know that finite sets can be covered by finitely many open sets. So what do? We take the finite cover of the finitely many points outside of U1, we add U1, and now we have a finite cover of S. Okay, so this shows that our set S is compact. So we can have infinite sets that are compact as long as they contain their limit points in this nice way. Excellent. Now let's get into a familiar example and try and see what our compactness says about the interval 0 to 1. So which of the following covers of 0, 1 has a finite subcover? Okay, well, looking at this first one, it's a finite cover. It's only got finitely many terms, so it definitely has a finite subcover. What about this second one here? This second one has a collection of endpoints that limit to 0. Right? So we're going to have something that looks like this with these getting closer and closer to 0. So if we take only finitely many of these, we're going to be bounded away from 0. We're going to be bounded by like 1 over n. So this is not going to have finite subcovers. Example C is quite interesting. Each of these has a fixed length, right? Each of these is 2/10 long. And then 0, 1 also has a fixed length. It's 1 unit long. So what do we have? At each point we have x, x plus a tenth, x minus a tenth. Right, so we have a centered interval at x around every point, and each of these has some fixed length. So if we take enough of them, we can cover all of 0, 1. So this will have finite subcovers. And it's interesting to ask how many need to be in this finite subcover. So these have length 2/10. So I think we need 5 or 6 of them to cover the whole interval. So we've got some examples of covers of 0, 1 where we have finite subcovers and where we don't have finite subcovers. So what does this tell us about compactness? The open intervals are compact. Are they not compact? So open intervals A, B are not compact. And the reason for this is that some covers have finite subcovers, some covers don't have finite subcovers. And compactness is a universal statement. We need for all covers there exists a finite subcover. So here we see that open intervals cannot be compact because they have some covers without finite subcovers. And now we're going to get into the topic of creative covers. So one of the things about compactness is that if you have a well-designed cover, you can get theorems kind of for free. So we're going to model this using a particular theorem. If S is a compact subset of the real numbers, then S is closed and bounded. So this is a theorem in 2 parts. We're going to prove the bounded part first, and this will model for us how to create covers with properties that we want. So we want a cover that says when you take a finite subcover, you should get a bound on your set. So we're going to consider the intervals centered at 0, from -n to n. Right? These are the intervals that grow out from 0. This covers the real numbers, and so it covers the set S as well. Since S is compact, this has a finite subcover, and that finite subcover is going to have some fixed size. It's going to be a particular length, big N. So S is going to be contained in -n to n, and therefore S is bounded. So what does this look like? What's this proof really doing visually? We have the real numbers. We have some compact set here, S. We have the origin 0. And now we're going to build a cover that detects that S is bounded. So here we go from -n to n. And when n is really big, we're going from -n to big N. And so if we have a finite subcover, there's going to be some big N that will contain our set S. So this cover, when you pick a finite subcover, gives us a bound on our set S. Okay, now we're going to move on to proving that S must be closed. And here we need a fair bit more subtlety in designing our cover. So we're going to show that S is closed by showing that if it has a limit point not contained in S, then that limit point has to be sort of isolated or separated from S somehow. Okay, so we're going to wind up proving this by contradiction. So suppose, for the sake of contradiction, that S is not closed. Then there is a limit point of S that is not contained inside S. So this point is somehow outside of S, and we're going to show that if S is compact, then it has to kind of be far away. So consider the following cover. So what are these sets? These are the sets of points that are bigger than 1 over n away from L. Okay, so the distance from Y to L is going to be big. It's going to be bigger than 1 over n. Okay, so any finite subcover will give some length, 1 over big N, such that Y minus L is bigger than 1 over n for all Y in the set S. Okay, so we're going to say that the distance from the set S to our limit point is bigger than 1 over big N. Okay, so L is farther than 1 over big N from every element of S, so L cannot be a limit point because it has to be contained in all these neighborhoods. Therefore, S is closed. It can't have a limit point that's far away from it. So what do these sets really look like? So here we have our compact set. Here is S. And we're saying there's a limit point here, L. And the sets that we've designed look something like this. So they are all of the points. So this is UN is all of those points so that this is bigger than 1 over n. Okay, so these are separated away from the limit point L. And if L was a limit point of S, it would have to be really, really, really close. And if we can get a finite subcover, then we can get some finite distance here. This distance of 1 over n. And that's going to say that L is isolated from S, that it cannot be a limit point of the set S. Okay, very creative cover. I recommend reviewing this, reading this proof through again, and trying to reword it, try and come up with an alternative description of the sets UN. Okay, now I want to talk about what happens when we look at the continuous image of a compact set. So this is just a background question, kind of a true-false question. Suppose that you have an open set and a continuous function. What do we know about f of an open set? So if you have a continuous function, you plug in an open set, what can you get out? So take a moment, try and write something down to see whether or not you've got this question. So it turns out that it depends on the function. There are functions, for example, f of x is constant, such that f of this open set is just some constant. Okay, the whole open set gets compressed down to a single point. So when we look at this on the real line, the image of our open set becomes a single point here. And in the usual topology on R, single points are not open. So it can happen that f of u is not open. So this statement is false. It is not necessarily an open set. Okay, so continuous functions don't preserve open sets. However, they do preserve compactness. So if S is compact and f is continuous, then f of S is compact. Super duper beautiful theorem, super duper important. It says we take a compact set, apply a continuous function, it stays compact. So this is sort of a property that's even nicer than being open. So what does the proof look like here? Well, I've drawn sort of a schematic function here. This is just our function f of x. Here's our compact set S, and here is our set f of S. And what we're going to argue is that open covers of f of S can be used to create open covers of S. So let's say that we have a open cover up here, right? We've covered f of S. So let Vi be a cover of f of S. Okay, so we have an open cover of the image. And now what we can do is we can use the properties of continuity to argue that this produces an open cover of S. So let Ui be f inverse of Vi. So the pre-image of an open set is open, so we're going to get an open cover down here of S. So Ui is open by continuity, and moreover, this produces an open cover of S. Okay, so now we have a potentially infinite open cover of S. And what we're going to do is we're going to use that to argue that it is a finite subcover. So by compactness, Ui has a finite subcover, and if we look at the image of those, then we get a finite subcover of f of S. Okay, so what do we do? What is kind of the idea of this proof? We take a open set here, we pull it back to S, and then we select a finite number of these that cover S to cover f of S. Okay, very, very lovely proof. Uses continuity in a very interesting way. Okay, now we're ready for the big theorem of the class. This is the extreme value theorem, and this is really a theorem about compactness. So it says, if you have a continuous function from a closed interval to R, then it has a max and a min. Okay, this gives us for any function on this interval, there's somewhere where it's going to have a max, somewhere where it's going to have a min. Very, very, very powerful. So let's prove it using compactness. So as you're going to prove on the handout, the closed interval AB is compact. Okay, so we have a compact set. When we take its image under a continuous function, we're going to get another compact set, which we'll call Y. Okay, so we take AB, we look at its image under F, we get another compact set. So we get that Y is closed and bounded by the properties of compact sets. And because it's closed and bounded, it's going to have a supremum and an infimum. So closed and bounded subsets of the reals have suprema and infima. So we're going to give names to those. We're going to say y max is the sup and y min is the inf. And these are going to be contained in the set y. So they're going to have x's that get sent to them. So f of x max will be y max, and f of x min will be y min. So these are points that get sent to the sup and inf of the image. So these are the values that become the max and mins. So what did we really use? We used the compactness of the interval AB. We used the fact that y is closed and bounded, and we're able to prove a very important theorem in first-year calculus, the extreme value theorem. So I hope this has given you a sense of the power of compactness and the amazing things that we can do with it if we can come up with creative covers. So thank you for participating. If you've got questions or comments, please leave them below. The handout for this talk is available online, as are the slides. Thank you for watching.